MongoDB with Kafka, which are two very hot technologies at the moment. So with that in mind, I'd like to transfer from yourself, Frederick, across to our next two presenters. We have Pedro Albuquerque from TransferWise. TransferWise are one of the hot fintechs here in the UK. I keep seeing your press releases, Pedro, in the Times, and every week there's something about your organization, which is fantastic. I know you're a senior database engineer there, and you're accompanied by Antonius Giannopoulos from Rackspace, who's a senior DBA there who focuses very much on NoSQL. So really want to hand over to the experts. So over to you guys. Look forward to this one. Thank you.
Thank you, Martin. Welcome to Using MongoDB with Kafka. I hope you have a great conference so far. We're going to start with some introductions. Martin already gave us a short one, but I'm Antonius Giannopoulos. I'm a senior database administrator in Rackspace Technology, and my primary focus is MongoDB. And we have Pedro with us.
Hi, everyone. My name is Pedro Albuquerque. I work as a database engineer at TransferWise for over 3 years now, and I've been working for about 9 years with open source databases, mainly MariaDB, MySQL, and MongoDB.
A quick overview of our agenda today. So we're going to start with a couple of definitions they're going to help us to deep dive into the use cases. We're going to examine topologies where MongoDB will act either as a sink or as a source. We're going to explain what those are. And we're going to cover a real-world use case from TransferWise. We're going to jump into MongoDB to Kafka connectors on random places within the presentation. And we have one slide at the end with recap and takeaway. So really quick, what is MongoDB? If you don't know, it's a document-oriented database, and it supports flexible JSON style schema. The use cases are pretty much unlimited. You can use it for any workload. It's the Swiss knife of NoSQL databases. It now supports transactions from 4.0 to 4.2, so those limitations are lifted. And if I would choose something, it would be like frequent schema changes and heterogeneous data. It has amazing capabilities, but at the same time, it acts as a permanent storage, and that's why I got the inspiration to make this presentation.
On the other hand, Kafka is a distributed low latency, high throughput, and fault-tolerant event streaming platform, and it is used to store stream of events durably and reliably. It's also a publish-subscribe messaging platform. At its foundation lies an immutable commit log, and from there, anyone can subscribe to it and publish data to any number of systems or real-time applications. Some services can use it in an asynchronous remote procedure style calls between services. It can also be used for event sourcing. Event sourcing involves modeling the state changes made by applications as an immutable log of events. Instead of modifying the state of the application in place, event sourcing involves storing the event that triggers the state change in an immutable log and modeling the state changes as responses to the events in the log. Kafka can also be used for real-time streaming and processing. In the next few slides, we are going to explore how MongoDB and Kafka form an ecosystem which is capable to scale. In this ecosystem, Kafka and MongoDB can have different roles that defines their relationship. For this presentation, we have chosen to use MongoDB to define the relationship. MongoDB as a sink means events or transactions or operations, you choose the naming convention, are first written to Kafka and then to MongoDB. MongoDB as a source is the exact opposite. MongoDB feeds Kafka with events. The combinations are unlimited, and the same applies to the topologies. MongoDB can act as both sink and source in the same topologies. The topologies can become really complex and have multiple branches. Let's start with use cases where MongoDB acts as a source.
So when MongoDB acts as a source, we think the most common use case is selective replication, extract and load, and extract, transform, and load. MongoDB does not support natively selective replication, for example, as MySQL does. So if you want to implement a topology that you want to only set a subset of your data to another MongoDB instance for various use cases like reporting or satisfy some kind of necessity within your organization from security perspective, you need to implement it yourself. So there is a Mongo to Mongo connector that it actually works and has built for this particular task exactly. But you can get into situations that you might run out of Oplog with this connector, or the remote side is not fast enough because sometimes we don't choose the same hardware. That's why I think we think it's a good idea to put a Kafka in the middle between the two Mongo sides. And Kafka is going to save all your events from Mongo. It's going to read from Mongo. It's going to write the events on Kafka and then propagate the events to the other side. So even if the other side is slow, you're not going to lose any events. Extract and load is pretty much the same as selective replication. You just get your data from one MongoDB and you load them to another. Extract, transform, and load is a little bit different because you're manipulating your data. You might want to hide some fields while you are doing the transfer. And obviously, on those use cases, you can have a different data store at the end. It doesn't have to always be Mongo. You can move from Mongo to MySQL or to Postgres if you need, but you're going to have Kafka in the middle. And we believe that it's way better if you have a topology like that you want to transfer data frequently from one database to the other, to use Kafka as the middleware. And now we're going to talk about a connector between MongoDB and Kafka. So connectors are a special type of software that allows you to sync MongoDB with Kafka. You can always write your own code. We're going to see that in the next few slides. But you don't have to always invent the wheel if you have simple use cases. So one of the popular connectors is Debezium. It supports both replica sets and sharded clusters, but relies on the Oplog, so you cannot have a standalone service for that. Installation is very easy. You can technically download the Docker container and run it in seconds. It can fulfill the selective replication because it has options to exclude and include databases and collections, so you can choose which one you want to be transferred. On the extract and load or extract, transform, and load, you can also find helpful the exclude list and rename list for fields. And you should be aware of two settings. The first is the snapshot mode, which can take initial and never. When you set that to initial, it's going to pretty much move all your collection data to Mongo. So we're talking about like 10 terabytes of data. They're going to move to Kafka. With never, you're going to start from scratch. So that depends on the use case that you have. And the other two, the tasks max and the initial sync max threads, they really play a part on sharded clusters when you have multiple shards and you want to set those parameters equal to the number of shards to utilize concurrency.
Another connector that is available is the MongoDB Kafka connector. Like Debezium, it supports both replica set and sharded clusters deployments, and you can't use it for standalone services. However, it comes with a very important difference. While Debezium can rely on its replica set Oplog, MongoDB Kafka connector only consumes for the MongoDB change streams. This feature guarantees access to real-time data changes without the risk of tailing the Oplog. And there is no extra operational tasks involved when the sharded cluster scales out. This is completely transparent. You can also perform selective replication. By default, this connector publishes the change data events to a Kafka topic that consists of the namespace from which the change originated. There's also the possibility to configure multi-source replication with events from multiple collections being published to a single Kafka topic. When it comes to extract and load, it is possible to filter or modify change events it makes use of the powerful MongoDB aggregation framework. So you can already imagine the many possibilities you can get here. The MongoDB Kafka connector can also be configured to copy existing data from collections to their associated topic as insert events prior to broadcasting change stream events. You can also throttle this copy by setting the max threads for the historical sync. Let's now see the use cases when MongoDB is used as a sync.
So the first use case we came with is throttling. Throttling is extremely useful in databases, in my opinion. Other people think that it's really bad. But on the events that we have listed on the slide, I think you're going to find it super useful, especially if you see unexpected growth events. I mean, it's way better to be able sometimes to serve a steady rate rather than getting downtime or an unavailability or slowness for everything. The need for throttling is there. I mean, MongoDB in 4.2 implemented something that they call flow control, which is pretty much throttling because it throttles the primaries in order not the secondaries to stay behind. And it's configurable. You can set it on and off, and you can set the number of seconds that you want to allow the lag. But again, the traffic is still going to hit your primary. And we believe that it's way better to prevent that traffic to hit the database before. So we think that's a good idea to implement that on the Kafka layer that you're going to have in front of your MongoDB. And when we're talking about throttling, we obviously talk about the write operations, right? Which is the strong card of Kafka. Kafka is way faster when it comes to writes from MongoDB, and that's by design because it's an append log. And on top of that, it scales way faster. You can add partitions, you can add brokers, you can add clusters. The most important one is all these changes, even if you add clusters, they require minimal application changes. MongoDB scales as well, and trust me on that. I work with MongoDB for 8 years, and it scales really well. But scaling takes time, especially in a live system. So, and you're going to get some overhead during that scaling because the balancer needs to move the data, and this data does not move physically; they move logically. So, if you try in MongoDB to add a new cluster, like a separate MongoDB installation, then you're going to get in trouble by trying to join the two clusters together if your application logic has been built that way. So how are you going to implement the throttling if you have a Kafka in front of your MongoDB? Really quick, there are two settings that they can help you: producer byte rate and consumer byte rate. So Kafka can actually rate limit the consumers and the producers. In this case, we care most about the consumers because the producers are those that they write on the Kafka cluster. The consumers are those that they're going to consume and write to MongoDB. So you can set some static values for those that most probably you have benchmark and you think are the optimal one for your cluster. But the most important one here that can allow you to build a dynamic topology is that you can actually change them on the fly using the Kafka config SH. And you can see the commands that I have at the bottom of a slide that you can actually change it straight away. And those changes are going to get effective straight away. And let's see how you can implement it with a few more additions. So first, you have to evaluate the MongoDB metric. You have to throttle based on something, right? In ObjectRocket, we usually use read and write queue, but you can use the latency, you can use whatever you like. We use Prometheus to monitor our MongoDB clusters. And Prometheus has a nice component which is called Prometheus Alert Manager that has tons of integration, and it can group alerts together. It can notify on resolution, which is very important. So let's see how you can implement that in the topology below. So you have your Prometheus Alert Manager, which monitors your MongoDB installation. And when it gets a queue alert, it sends that to your favorite integration. It might be Kafka, it might be whatever. It must be an integration that can run the Kafka-config. .sh. So it sends the alert, then the integration decides what to do. Most probably, if you get a queue alert, it's going to reduce the amount of consume rate a little bit. And then it might send another alert, and the integration will do the same, etc. But when it sends the resolution, it's going to recover it. It's going to return to default. Another use case we came with is workload isolation. And Kafka can handle some workloads way better than MongoDB. And let's see that with an example. Let's say we have a very successful event like Percona Live. And most probably those events have an app. And on the application, the users do interactions with social media. And the first thing when you open the application, you want to see the latest interactions. So you can serve those interactions if you have a MongoDB to Kafka, Kafka to MongoDB topology by Kafka, because this is native workload for Kafka. The events come, they're ordered on the Kafka, so you can serve them straight away. With Mongo, you can do more sophisticated things. You can like serve what aggregation, you can serve aggregations like what's the hottest talk, which one got the most votes, which one, which keyword is with the most references, these kind of things. And here is an example how you do it with Python. I mean, we know that in Python, Java is the king, but you can see my coding skills in Python that people say that I'm good on. So imagine what's going to happen if I try that in Java. The important lines here are highlighted. You pretty much get from Kafka the latest offset. So you go at the top of the queue, and then you just reduce the number of records you want to display to the client. So you give the latest 10. Yeah, don't forget to exit, because that stream over there, if new records come, it's going to feed them to the client. We try to keep it Kafka native on this presentation, but I couldn't resist to mention that. So Kafka has a rich ecosystem, and there's a component called Kafka Streams, which can do continuous aggregation for you, and it supports functions like windowing, so it can do time-based aggregations. So the continuous aggregations are very useful in use cases where the raw data have no meaning to you, like a meteo station that you might want only the max and the mean for every hour. You don't care about the individual metrics. Most probably not on your commercial application. It might be a scientific application, maybe. Or website statistics. You might care about the rate every minute or every hour, but not for the hits that you got every second. So the use cases are unlimited if you mix and match. Another use case we came with is called journal. So in databases, data recovery is a user request. So a lot of things can go wrong. I mean, you can have a human error, an application bug, hardware failures. So the most tricky part on those recoveries is a partial recovery, when you have to do a couple of documents from MongoDB. Someone ran an update and you lost your data. If you need to do those partial recoveries, most probably you have to extract the entire backup and then replay from the Oplog. The idea we built here is why you don't just replay the changes from Kafka instead. And we came up with an example here. Let's say that we have an application that our users save their playlist in MongoDB within an array of songs. So one of our customers lost its data. You can see that on the top. DB users do fine. We have only one customer. We're not very successful yet. So now if you want to restore his data, you have to go to the backup and then replay the Oplog. But if you have all the records on Kafka first, if the songs first written to Kafka and then to Mongo, all you have to do is you go to the beginning of the stream and you replay everything. And then for that particular customer. And then you just do an add to set to the array. So even if he has a partial loss, you just restore the items that are missing. If you don't keep all the data, you might do a partial restore. You might not have all the data, but that sometimes will give you time to go to the backup and do the manipulation to get that customer records. Sometimes might not be handy, maybe with financial transactions.
Let's now look at how MongoDB and Kafka are used by TransferWise activity service. In TransferWise internal definition, an activity is something that the user has done or something that has affected the user. Usually, an activity represents an action like send money, pay by card, top up your balance, for example. Any of those actions are represented in activity domain as action type, and they have different status and categories. Activity service is the TransferWise microservice that provides information about all activities done in TransferWise, like transfers, balances operations, card usage, and etc. It provides a way to view and search the customer activity list. This service listens for activity Kafka events, transforms and organizes the information, and finally stores it on MongoDB. The integration between Kafka and MongoDB in activity service is done with spring-kafka and can be logically divided into producers. These are the microservices responsible to serialize and send activity updates and deletes by calling an API made available by the activity service. These are the different topics used for this service. 2 are used by other services to send activity updates and deletes, and the other one is used internally by activity service to help processing batch activities. Then we have the consumers that will take care of reading from the Kafka topics and deserialize messages. And finally, the processes will take care of, from other things, sync records into MongoDB. Let's look at spring-kafka configuration used for the activity updates flow. This is a sample of a producer configuration that activity service has put in place. To create messages, first we need to configure a producer factory, which sets the strategy for creating Kafka producer instances. Second, we need a Kafka template, which wraps a producer instance and provides convenient methods for sending messages to Kafka topics. In this code snippet, we are configuring for a model two very important properties. The bootstrap servers config is where you define host and port on which Kafka is running. And the key serializer and value serializer class configs define the serializer class to be used for the key and value. Spring-kafka provides JSON serializer and JSON deserializer implementations that are based on the Jackson JSON object mapper. It allows us to convert any Java object to bytes array. Then, to send a message, all we need to do is first to serialize the message, and then call the send message method with the message and the topic name. Spring-kafka also allows us to configure an async callback. We can receive the result of the send method and do some work within an execution context. When consuming messages, we need to configure a consumer factory and the Kafka listener container factory. Once these beans are available in the Spring factory, plain old Java objects-based consumers can be configured using the Kafka listener annotation. One important note is that the consumer needs to use the same serializer class used by the producer to be able to deserialize the message. The enable Kafka annotation is also required on the configuration class to enable detection of the Kafka listener annotation. Finally, we then write a listener to consume, in this case, the activity update messages. For TransferWise activity service use case, MongoDB Kafka connector could have helped reducing the boilerplates. It would be possible to configure both processes and consumers at connector level with ease, without the overhead of coding them on Spring-kafka. However, the activity engineering team didn't adopt it because most of the TransferWise engineering team has years of experience with Spring-kafka and wanted to speed up with development. Adopting this connector would be introducing a new way to integrate Kafka. Nevertheless, we'll be evaluating it soon and we'll share the results with you later. Let's now look at some of the most important settings for the MongoDB Kafka sync connector. There are 3 required main configurations for this connector. a list of Kafka topics that the sync connector will watch, the name of the MongoDB databases, and the collection the connector will write to. Another important setting is the ability to handle parallelism. However, specifying a value greater than 1, you enable parallel processing of the tasks. If your topic has multiple partition logs, messages may be processed out of order. The converter setting specifies the deserialization method for data it reads from a topic. It is important to have a well-defined deserialization method. In Kafka, producers write structured messages to a Kafka cluster. Similarly, consumers read these messages from the same cluster. When different groups are in charge of writing and managing producers and consumers, one major pain point can be the coordination of the agreed message format. Kafka is not aware of the structure of data in key and value records. It handles them as byte arrays. But systems that read records from Kafka do care about data in those records. So you need to produce data in a readable format. So the data format should be compact, be fast to encode and decode, allow evolution, and allow upstream and downstream systems to upgrade to new schemas at different times. JSON is not a compact data format, and it is slow to parse. Apache Avro, on the other hand, is a fast serialization framework that creates relatively compact output. But to read Avro records, you need a schema that the data was serialized with. Now, where to store the schema? The schema registry is the answer to this problem. It stores your schemas, including all their versions. When you send Avro messages to Kafka, the messages contain an identifier of the schema stored in the schema registry. When sending a message, the serializer will make sure the schema is registered, gets its ID, or register a new version. When reading a message, the deserializer will find the ID of the schema in the message and fetch it from the schema registry to deserialize the Avro data. With this connector, it is possible to define the field projection by creating block or allow lists. The connector can be configured to ensure messages including a value for the underscore ID field. It uses the Debezium object ID strategy, which generates a new Debezium object ID for the underscore ID field if it doesn't exist. It is also possible to define a custom value for the underscore ID field using the document ID header post-processor. It can also be configured to send messages that cannot be processed to a dead letter queue. The connector sends invalid messages to this queue in order to allow manual inspection, updates, and resubmission for processing.
And some recaps and takeaways. We presented a couple of use cases for how MongoDB and Kafka can work together from the eyes of a DBA architect. I mean, obviously, there are way more use cases for these two data stores, and the more you get involved with the Kafka ecosystem, which is super rich, the more it expands the use cases. Connector is your friend, but you can build your own connector like TransferWise did, and it works really well for them. And we consider these two products very mature for complex projects. I mean, you see that large organizations like TransferWise are using them together successfully. We want to thank you for attending. We want to thank Percona for letting us present to that conference. And we want to give a big thanks to these two folks on the bottom of the slides. And if we have time for questions, we're open, or you can reach us on Slack.
That was a fantastic presentation. So many thanks, Pedro and Antonius. We don't have time for questions. There are a couple on the Slack, and we'll make sure that they're responded to, because everyone's very interested in Mongo and Kafka and what else could be done in this use case. But we do need to move it on. So thanks again